Hi, my good friends. This is Frazier Nyasulu, Chem 1520, lab number 6. Well, another lab involving some kind of equilibrium constant. They just seem to show up everywhere. Last week, Henry's law's constant and the equilibrium for the iron thiocyanate reaction. Today, what's our goal? Ka and Kb. A for acid, weak acid ionization, and weak base hydrolysis. What are the constants and how do you find them? We're going to do it two ways. By measuring the pH and the conductivity. Let's talk a little about measuring conductivity. You've seen this plot here, this figure from the 1510 lab manual. You have an aqueous solution. There's some electrodes here, metal plates. There's a solution in here. You pass, in this case, DC, at least for the sake of argument, and ions flow one way or the other. That constitutes a current, and that's how you measure conductivity. You're applying a certain voltage, you're measuring a certain current, and these plates are a certain area. In the old scheme, we used to do this. This is platinum here, some platinum electrodes, platinized platinum. So platinum is nice and shiny, but you make it kind of powdery and deposit on the electrode, so you have a huge surface area of contact between the electrode and the solution. You put these electrodes at a certain distance, you know what the dimensions are, and you use that to measure conductivity. These days, you use this for measuring. Well, I'm turning it the wrong way. All right. There it is. Moving right on. So how is conductivity defined? Again, this is a reminder. You apply a certain voltage and certain current flows. And as you might expect, if the current is high, the conductivity is high. So that's why current is on top and voltage is down here. And for whatever reason, let's see if I can pick up a pen again. Pointer. Uh-oh. I'm looking for pointer options. Anyway. All right, so this here, current over voltage, is called a Siemens, S, and this is distance meters, so conductivity Siemens per centimeter. In our case, since we're measuring whatever we measure, we'll go micro Siemens per centimeter. Micro Siemens per centimeter. You guys have done that already in 1510. So what are we going to do? 1 Ka for 3 acids. Again, doing it two ways. Conductivity, pH. For the base, how about we just do one? Our favorite, ammonia. Then going to measure the pH and conductivities of various solutions and see if we can explain where that conductivity comes from. Some of these will be everyday solutions. All right. So now what we're going to do is figure out a way of this conductivity and getting to Ka. So suppose you measure conductivity. As you know, it depends on concentration. So the higher the concentration, the higher the conductivity. Well, let's divide by concentration. So conductivity, molar conductivity. Molar conductivity is conductivity versus concentration. Guys have done that in 1510. Now, if we're dealing with an acid, turns out that the fraction of acid dissociated or ionized is equal to this here, the molar conductivity divided by the conductivity at infinite dilution. We know what this is, and we can calculate it above. You calculated it last week or 2 weeks ago. But where does lambda at infinite dilution come from? And how does it help us in this course? Well, here's the deal. Take an ordinary thing like, for example, I think this happens to be HCl. Plot the molar conductivity versus concentration, and you'll find, strangely enough, that I need to find my pen. Create ruler, no. Oh, come on. I give up. Maybe I should be in. All right, maybe it will allow me to do now that I'm in full view. Pointer options, great. Pen. All right. So again, here this is molar conductivity, this is lambda sub m versus concentration, or in this case square root of concentration. It looks like this, and this is kind of strange because you'd expect it to be just straight like that. I mean, just with a zero slope. But it turns out because the ions associate at higher concentration, they kind of hold each other back. Don't go to the other electrode. Come on, slow down a little. Hook up with me. Stay with me a little bit. So they kind of interact that way. And so the conductivity actually goes down slightly. And if you do the molar conductivity, it increases as the concentration goes down. If you were to extend this line all the way up to here, you have the conductivity at infinite dilution, where the ions are essentially not seeing or recognizing the presence of the other ions. So, in this case, if this is the plot, and this is the equation of the line, here is lambda 0. The conductivity at infinite dilution. So, going back, hey, if we can find this, measure that. If we can find this for the particular weak acid or species, then we can calculate alpha. And it turns out that'll take us to our goal. What's our goal? Ka, Kb. Moving along. All right. Take acetic acid. Call that our favorite acid. Let's see if we can move this out a little. All right. There it is. The weak acid ionization. This kind of goes on a little way to the right-hand side. That's why we call it a weak acid. Suppose the initial concentration is C before ionization. So 0, 0 on the other side. And then if we follow the previous definition, then this here, the change is alpha C, because alpha is a fraction that dissociates. So minus alpha C, alpha C, alpha C. Then the equilibrium concentration is this minus the change. Aha, the ice table. You end up with this here, end up with that. Guess what? If you enforce the definition of the equilibrium constant, Ka, you know it to be that there. Okay, it's not giving me a pen. You know it to be this. You end up with this. Haha. So, we'll know what the concentration C is. If we can find what alpha is, we can calculate the equilibrium constant using conductivity. Great. pH. You know that already. Defined in your text many times. Same thing here. Acetic acid. If we now say the change is minus X, then we end up with this equation here. All right. Ka is equal to X squared C minus X. We know what C is, the initial concentration of the acid. If we can find what X is, or the hydronium concentration, then we're good to go. But we can measure the pH, and from pH we can calculate the hydronium ion concentration. Yeah, there it is. We can calculate the hydronium ion concentration after we measure pH. And since this guy is equal to that guy, we know that too. And if we know the original C, we can subtract the X, which happens to be the hydronium, and we can calculate Ka. Good. Why do it two ways? We can compare the two and figure out which works better and why. That's part of your scientific training. All right, base. Base hydrolysis. There is a reaction. You create OH minus on the other side. Base hydrolysis. Okay, same thing. Initial, change, equilibrium. I stable. End up with this thing here. The only difference here is that X is OH minus. But we're measuring the pH. Sure, if we know the pH, we can find OH minus. pH plus pOH is equal to 14, and we can do the little arithmetic that gets us to the right expression. So, by measuring pH, we can find Kb. Let's get the show on the road. Experimental setup. We've talked to you, you've used this. This is a picture you've seen in 1510. The metal electrode that measure conductivity in here. It's got to wash through that little hole there, right? Okay, so here's our setup. Why two of those? Because in our case, we do it for the same solution. Why do it in sequence when you can do it in parallel? Aha. So, conductivity sensor there, pH sensor hooked up here, and then the data logger will give us both. What a wonderful life. But instead of doing it for one solution, we're going to do it for multiple solutions. And then we can calculate Ka or Kb and show that it is a constant. Just like we did last week for the iron thiocyanate reaction. All right, moving along. So here's a way to do it. This is our entire setup. We'll put a known amount of water, 60.1 or whatever the volume is of distilled water. And then we're going to add an aliquot, a non-aliquot of a non-concentration of acetic acid or ammonia, whatever it is. And then we're going to measure those corresponding things. And then from those, we'll do the experiment. Okay. So now, very important, especially for the conductivity sensor, because the sensors are embedded, that when you so you add an aliquot, you stir, then you move this conductivity sensor up and down so that the solution within the measurement area is the correct one. Other than that, add, measure. Add, stir, measure. You can do the 10 or so measurements of the two of those in a few minutes. 10-15 minutes, you're done with one reagent. By the way, make your life easy. One person does the additions, the other person records the data. Don't stop to record the data if you're the one doing the additions. You can get the data afterwards. Save a little time by thinking about what you're doing. Moving right on. You'll have to calibrate the pH sensor. There are directions for that in the lab manual. After you're done calibrating, come back and measure the pH of the standards. 1, 2. Is it recording the right values? If that's true, you're good. If not, go look back, look at the directions, see if you missed something. And if it fails the second time, then talk to your TA. Calibrate the pH sensor. How about calibrating the conductivity sensor? Well, that has to do with just dipping it in water, distilled water, for a little while so that it cleans itself. I call it, it wakes itself up from slumber. It's been sitting there completely dry for months, sometimes years, so it needs to hydrate properly. And you should read in a low conductivity, typically 50 microsiemens per centimeter. For distilled water, that means it's good. Then you make the measurements. All right. Conductivity sensors, you know, has 3 scales. You always start with the most sensitive first. If that fails, you go to the bigger guy, 1,000 to 10,000. If that fails, you go to our biggest scale, 10,000 to, I think it's 100,000. And then, so you start with acetic acid, and you add, 60 ml of water, then 1 ml aliquot of 1 molar. Then you repeat with with phosphoric acid and ammonium. Should have the conductivity and the pH probe. Safety issues? Sure, acetic acid. There are acids, the weak acids, but all the same, keep your goggles on. at all times. And it should be done with this lab in it took me 23 minutes. It'll take you twice as much, so it should be done in about an hour. May I suggest that you then hook up with your buddies and do all the calculations, and be done then within the 3-hour time span. Why don't we take a look at the spreadsheet? How do I get there? Yeah, there we go. There we go. See, that's our spreadsheet. Too big. All right, see if I can get there. All right. Let's decrease the size a little bit. So here it is. The concentration, whatever that concentration is, the order that you put in. These are the 1 milliliter aliquots over here that you're adding. And you'll calculate whatever the concentration is based on this volume and whatever you're adding up here. That is HCl concentration. These are the measured conductivities. This is measured pH. And using the equations that are in the manual and elsewhere, you can do the calculations. In this case, when I determine this conductivity at infinite dilution. So it turns out that plotting the square root works better than plotting the conductivity itself. So here is the conductivity versus concentration, and up here is actually down here is the molar conductivity versus the concentration of square root. And so in this case, one could is there a pen somewhere? I don't know. It's not giving me a pen option. Anyway, one could then draw the line here. There's a curious point that's up here. Draw the line like this, all the way over here, and find out the conductivity at infinite dilution. That's just to give you an idea of where these things come from. In this case, we'll be providing the conductivities at infinite dilution. So here's acetic acid. All right. Calculated concentration based on the concentration and the volume here. And you have all this data here, and then you can do all the calculations, molar conductivity, and from that calculate the fraction. Here's the conductivity at infinite dilution. So remember to fix that when you use it in the plotting, so that it doesn't roll in Excel. And then these two here, the H plus and the acetate, are the same, and you can figure out whatever the unionized acetic acid, and then look at Ka. And then here, look at this. Look at these values here, and one can find the mean or standard deviation of these and say they're about constant. So this hypothesis comes out okay. Ka is a constant. So that's based on what? On conductivity. Here's a calculation based on pH. Same concentrations as before there. Here's the data, the pH, and then you calculate these according to the equations above here, or you can look them up in the mind, or better yet, be able to reason them out yourself. And then look at whatever these values look out to be, about 10 to the minus 5 here, if you round off the 9 something to 1 to 10, and so Kp seems to be a constant as well, at least based on my data. And then I'll ask you to do a few questions. You'll note in this case, and this is important that I remind you this, whenever you have a weak acid conductivity versus the concentration, it curves. It's not linear. Why? Because as you know from the, it's even in your textbook, can't quote the page, but it's in the percent ionization actually decreases with increasing concentration. So it's high here, so it should be line should be going up like this, but because it decreases, it flats up like this. If you had a strong acid, it would be perfectly linear. Weak acids curve when you plot conductivity versus concentration. So I'll ask you a few questions there. Phosphoric acid, same thing, same calculations, same reasoning, and here. One of the people drew a straight line, but as you can see, it actually is a nice curve there. And again, it's because phosphoric acid is a weak acid. And then moving right on, what am I missing? The last one is ammonia. Calculations are pretty much the same, except that in this case you measure pH and you're looking for OH minus, so be able to do the translation from one into the other and show that Kb is also a constant. And then we'll ask you again here for the conductivity of ammonia versus concentration. It curves because again ammonia is a weak base. Short, sweet lab. Work it through. In this case, look at the quality of your data and see why it is that the data comes out that way. Make sure you get good data before you leave. And then, as per my suggestions, that is if you listen to me, work out the Excel and do the calculations with your friends in tow so you can discuss, no copying from each other, and correct each other and reason things out and ask questions of your TA or myself, and then be able to hunt this up in the 3-hour time allocated. Love you guys. Have a great day.